Welcome to Eager Space. This is part one of a multi-video series on orbital debris and the Kessler syndrome. On the 10th of February in 2009, the Iridium 33 communications satellite and Cosmos 2251, a Russian Strela 2M military communications satellite, had an unexpected meeting, colliding with each other at a speed of 11 kilometers per second, or 24,000 miles per hour. The two satellites collided over northern Russia at a time when their orbital tracks were nearly at right angles to each other. The collision created debris fragments in slightly different orbits than the original satellites. The U.S. Space Surveillance Network tracks all orbital bodies in low Earth orbit that are 10 centimeters or bigger in size. At least that's the public number that I could find. It seems likely that they are better than they say. Their software can associate debris from a collision with the source of that debris, though it can take weeks or months to do the association. They cataloged 1,714 pieces of debris from Cosmos 2251 and a further 657 from Iridium 33, for a total of 2,371 tracked pieces of debris. In the 17 years since then, many of the pieces of debris have re-entered, leaving 640 from Cosmos 2251 and 121 from Iridium 33. The ones that are left are in higher orbits where it will take 25, 50, or even 100 years for the orbit to decay. That is because the satellites were in orbits at about 800 kilometers, where atmospheric drag is low. These numbers are only the count of the large objects, those at least 10 centimeters in size. NASA estimated the debris population at smaller sizes using sampling radars, and their estimate is roughly 10 times those numbers at 1 centimeter of size, and roughly 100 times those numbers at half a centimeter. Collisions like this were exactly the situation that Donald Kessler and Burton Corpillay were discussing in their 1978 paper, Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. They developed a model for what the future would look like at various launch rates: 320 new objects per year, 510 new objects per year, and the 13% growth rate per year that existed when they wrote the paper. That chart does show exponential growth, and that's what people are talking about when they mention the Kessler syndrome. If the exponential growth gets bad enough, it may be difficult to keep satellites in orbit functional. But surely this can't be the only example. What about all the other orbital collisions? As of 2022, the latest update from the NASA team that tracks these things, there were 5 other accidental collisions. They were all collisions with other fragments, not other satellites, and they generated 59 tracked fragments combined. The system appears to be working fairly well. One reason is that active satellites can dodge out of the way. The U.S. Space Force tracking system continually keeps track of objects in Earth orbit, and the Space Force has a website that publishes that data. It publishes data in what is known as a two-line element. The two-line element contains not only the information to know where the object is now, but enough information to predict where the object will be in the future. Do that across all of the objects, and you can make predictions of conjunctions, when satellites get close enough to each other that collisions are likely. Because that TLE catalog data is published, a company like Iridium can take the TLE information from all the cataloged objects, update the info on their satellites with their internal data, plus any movements they plan to make, and feed all that data into a conjunction prediction algorithm. They will end up with a chart like this one. The green circle shows the prediction that Iridium 33 and Cosmos 2251 will come within 100 meters of each other on the day that they collided. But note that it's not the closest prediction for that day. There are other Iridiums that are predicted to come even closer to other satellites. This did not look like a big deal. The Space Force also does conjunction prediction, but for that process, they use a higher accuracy catalog than the TLE, one that allows the future path of a satellite to be predicted with much more accuracy. When they predict that satellites might collide, they send messages to the satellite owners. What we have is a systems problem. The U.S. space tracking folks are more accurate in forecasts of the future position of satellites because they have the high accuracy catalog. What they don't know is any movement plans for the satellites. The Iridium folks know exactly where Iridium 33 will be because they have planned to move it slightly, one of the normal small movements to keep the constellation satellites where they need to be. They only have the TLE catalog data, so they can't predict the path of Cosmos 2251 with high accuracy. Neither group has full information. They both think there will be a close pass, but it's only when Iridium 33 goes off the air that the Iridium team realizes that something very bad has happened. If the conjunction prediction is done with the higher accuracy catalog data and the planned movement of Iridium 33, we get the following graph. It's pretty clear that there's a significant issue on February 10th, and if this was known, Iridium would have changed their movement plan. There are 3 changes made to prevent collisions like this one in the future. The SpaceTrack folks now publish the high accuracy data. Satellite operators can submit orbit and position data about their own satellites, and operators can submit movement plans to specify how the orbits will change. These were all good things, and it seemed that the system was working well. But then the world started to change. In the old world, the majority of commercial satellites lived in geostationary orbit, with a total of about 600 satellites. That sounds like a lot, but the assigned orbital slots are more than 1,500 kilometers, or 900 miles from each other, and they are all orbiting in the same direction right over the equator, so the chance of collision is small. They mostly just keep to themselves. Iridium obviously changed that a bit, with 75 satellites in low Earth orbit, but the system adapted. Then Starlink showed up, initially with 4,425 satellites proposed, and now pushing beyond 10,000 satellites. They entered a world with only 1,500 active satellites in total, and the Starlink satellites occupy different orbit altitudes and inclinations. They are all over the place in low Earth orbit. There have been a few reported issues. China reportedly had to move their Tiangong space station twice to avoid Starlink satellites, and ESA also had to move a spacecraft to avoid a collision. One of the underlying issues is that there is no space traffic control. The US Space Force does a lot of work, but there's no mandatory system, and going from 1,500 active satellites in 2015 to 12,000 in 2026 has made things a lot harder. To their credit, SpaceX has built a good conjunction analysis system and adopted a high standard. They will move a Starlink satellite if they estimate the chance of collision is more likely than 1 in 100,000. That's an order of magnitude better than most satellite operators. They move their satellites all the time, performing 300,000 avoidance maneuvers in 2025. But 10,000 Starlink satellites is just the tip of the iceberg. Starlink initially had a target of 34,000 satellites, but Gwynne Shotwell recently said they probably won't need more than 20,000. Amazon Leo has already started launching satellites for their 3,200 satellite constellation, and Blue Origin's TerraWave is targeting 5,400 satellites. Together, those additions will roughly double the current population again. If we look at where they are in orbit, SpaceX has large populations at 360 kilometers, 480 kilometers, 541 kilometers, and 574 kilometers. They've said that they're moving 4,400 satellites from the higher orbits at about 550 kilometers down to 480 kilometers in 2026. The Amazon Leo satellites are destined to live at 590, 610, and 630 kilometers. They are currently working on the 630-kilometer shell, as that will give them the most coverage. TerraWave plans to put most of their satellites between 520 and 540 kilometers, though they also plan to put 128 satellites at 8,000 to 24,000 kilometers. We can add in some numbers on the expected decay time for an average satellite at each altitude, and we can see there is a broad range in expected decay time. The FCC requires that LEO satellites re-enter within 5 years of the end of their mission. That's roughly at 500 kilometers, and the Starlink change to move most, or perhaps all, of their satellites below 500 kilometers means that even broken satellites will re-enter within that time frame. It also means that any orbital debris created from collisions will re-enter fairly quickly. The TerraWave and Amazon Leo satellites are higher, and will therefore need some sort of active deorbit system, and collisions there will become more problematic, as the debris will stick around longer. These are just rough numbers. The actual numbers depend on the specific geometry of the satellite or debris and the amount of solar activity, as that causes the atmosphere to expand and contract. These discrete orbital shells look like a great idea. If Starlink is down at 480 kilometers, there should be no interference with the other providers. The world, however, is a lot more complex. This is what the Starlink population looks like in March of 2026. There are big spikes at the altitudes that I showed, but there are also quite a few satellites in between, as new satellites move into their orbital shells and old satellites move out of them. That makes the debris environment much more dynamic than it might appear. And as I said, these new constellations will roughly double the number of satellites in orbit. But even with that, the system seemed doable. Everybody will need better tracking, better prediction, and the ability to move around. But with cooperation, it can probably work. Now we have the data center satellites, with Blue Origin Sunrise proposing 54,000 satellites, NVIDIA's StarCloud with 88,000 satellites, and SpaceX's unnamed constellation that I'm calling Starthink with 1 million satellites. Sunrise is from 500 to 1,800 kilometers, StarCloud from 600 to 850, and Starthink from 500 to 2,000 kilometers. SpaceX says that some of their satellites will be in 30-degree orbits, with the rest in sun-synchronous orbits. Sunrise and StarCloud are all planned to be in sun-synchronous orbits. This is a weird assertion because sun-synchronous orbits are quite constrained, and there are a total of 4 of them between 500 and 2,000 kilometers, at 567, 894, 1,262, and 1,681 kilometers. The point of sun-synchronous is to have repeatable lighting on the ground to make image analysis easier. But the satellites are not designed for imaging, so it seems unlikely that they are actually going to be sun-synchronous. I think they just mean polar-ish orbits, where they get a lot of sunlight. This is particularly true for StarCloud, as their announced orbital range does not include any sun-synchronous orbits. Looking at satellite populations, let's start small and guess that each of them are only going to launch 25,000 satellites. That will roughly triple the number of satellites above what the LEO communication satellites added, up to perhaps 100,000. There are some big downsides to this. To avoid collisions, the satellites will need to be dodging all of the time. Even a day without movements could lead to a collision. Solar storms might interrupt communications, so you might not be able to talk to your satellites. We see cloud outages fairly often. You can't have anything like that on your network. Given history, we should expect one or more of these companies to go bankrupt. Who keeps the satellites dancing to avoid collisions if that happens? And their high altitudes means long-lasting debris. There's one proposal in particular that has me concerned. StarCloud has said that at least some of their data centers are going to be 4 kilometers on each side. The current Starlink satellites have an area of roughly 116 square meters, and SpaceX is moving each satellite a few times a month to avoid debris. The proposed StarCloud satellite has a surface area of 16 million square meters, or roughly 46,000 times the area of Starlink. It will have conjunctions every day, if not every hour, and because of the size of it, it cannot easily dodge the other satellites. Instead of moving a few hundred meters, it will need to move kilometers. Such a structure is going to get hit, and hit often. It's hard to take people who make these sorts of proposals seriously. And what about the smaller and more numerous untracked objects? A 1 centimeter dense fragment has enough kinetic energy to take out a satellite, at which point the satellite is too tired to dance. As far as satellite collisions are concerned, where do you end up on the Kessler syndrome panic scale? When I started working on this topic, I was in the middle. The current systems have done well preventing accidental collisions like the one with Cosmos 2251 and Iridium 33. Starlink has reached 10,000 satellites, and Amazon Leo and TerraWave are smaller. It's not totally fine, but it's probably workable. The orbital data center plans have pushed me a fair bit to the right. There's enough hype and investment that it seems likely that some of them will fail, and there will be satellites in orbit without keepers, and that could be quite bad. And that's all for part 1. Next time, we'll look at collisions that aren't accidental. The song for this video is Dreaming While You Sleep off of Genesis's 1991 album, We Can't Dance.
Eager